Hello everyone. So again, this is, I think this is our third installment. This is our third installment, and we are going to try to again talk about slopes and areas. And what I'd like to do is I would like to explain this in the context of uniformly accelerated particle model. Okay? So if you recall, when we did SELF 05 and SELF 06, or Lab 05 and Lab 06, this is what we obtained. We obtained, or we got a curve instead of a straight line. Well, this is the position versus time graph. And I hope you remember in LogoPro, you guys kind of went, like this, with that. Now, at this point, we introduced the idea of instantaneous velocity, meaning the velocity at any given instant, and we said that it has something to do with the slope. And as you can see here, the slope of what? The slope of the tangent. Okay, so if we decide, okay, that we're going to be drawing, let's say, the time in the x-axis and the velocity in meters per second in the y-axis, then at this point, let's assume that we are dealing with a situation where, we're starting with a certain initial velocity v sub xi. So that means we're starting, let's say, with some velocity over here, okay? Oh, sorry, I want to be consistent. We're going to use green for velocity as usual. So now, as we move to a new point, we're going to have, as you can see here, the slope of my ruler here is steeper. Therefore, it's going to be a higher velocity value along the velocity curve, diagram. So, and we'll keep on going like this. So as you can see, our velocity is increasing steadily in a straight line fashion, as you can see right there, like that. Okay, so, well, we already talked about the idea of what the slope in this case represent. Well, this is the change in the v over the, and this is the change in t, and we explained then that a sub x is going to be the slope by definition for this one. So delta v silly me, come on. Okay, delta v sub x over delta t, and that would be the meaning of the slope in this regard. But the thing that we would like to discover is what would the area represent? And that's what we're going to try to do next. So what I'm going to do is I'm going to try to go ahead and just copy this graph right here, if I could. Okay? I hope it did. And if it did not, that's okay. We'll figure out something. So let's copy it. Let's go to the next slide. Let's set our grid. And then we're going to be pasting that. Here we go. Yep. And I'm not going to worry about the area now for that. And then I am not going to be a little bit concerned about this for now at least. Okay? And what I'd like to do is I would like to take this and put it a little bit higher so you would be able to see it a lot better. Here we go. So look at that. And then what we're going to do, we're going to get rid of the slope information, and we're going to focus only on the area now. So, let's say I go at a certain time t later, okay? And at this point, I am going to try, at a certain time t later, I would like to be able to determine what does the area inside here represent. So, let's set an area of some sort. Here we go. We've got an area there. But the interesting part now is that this area is a parallelogram. No, a trapezoid. Silly me. I know my geometry. Anyway, so what I'd like to do is we're going to split it into two smaller, areas. So we'll call this area 1, and we'll call this area 2. And then we're curious as the total area, which is equal to A1 plus A2. So we're going to try to see what these two areas are going to be representing eventually. But before we do that, what in the world does this point represent here? Well, it's going to be representing my initial velocity. And then this point here is going to correspond to my final velocity, v sub x sub f. Okay, so in order for me to determine an area, I would have to have two dimensions. So I've got the t here, and I've got vxi there. Therefore, area 1 is going to be equal to v sub x sub I times the time t. Cool or no cool?
Cool.
Very good. Now, at this point, we would like also to determine area 2. Well, area 2 here is a little bit tricky because this dimension right there is not my VXF. VXF is this whole thing. So, I need to determine just this part right here. What is it equal to? Guess what it would be in terms of VXF and VXI? Call 1, call 2, call 3. I hope you answered that it corresponds to this here, corresponds to VXF minus VXI. And if that's the case, then this is an area of a triangle, so it would be this, this dimension, the base, multiplied by the height, which is this quantity here, divided by 2 or multiplied by 1/2. So A2 then is equal to half, between parentheses, the height thingy, VXF minus VXI, and then multiplied by the time. I'm going to change the colors because I think green is hard to see. So I'm going to work with this, I don't know, this cool pink. There we go. Okay, so at this point, I've got, this is already kind of set. I've got my VXI and T. This, on the other hand, I have this VXF that I need to make sense of. Well, if I go back to the previous line and realize that this is the equation of a line that is given by y equals mx plus b, but that's ugly math. We want to do it in the context of physics, so it would VXF equals the slope, which we establish is the acceleration. So it would be a sub x times t, plus the, whatchamacallit, the intercept. Well, the intercept is the initial velocity right there, so Vxi. So technically, I can substitute for Vxf this wonderful whole relationship. Let's put it over there. So we would, instead of that, we're going to put this in here. So we're going to have A2 equals half. And I've got this Vxf, which I'm going to substitute for it, A sub x t plus V sub x sub I. But then I still have this minus Vxi. So minus Vxi. Multiply the whole thing by the t over there. Well, you know your math to realize that Vxi and Vxi, when they are subtracted, they cancel each other out. So I end up with my A2 being equal to half A sub x t times t. That would give me t squared. Now, I've got this. I've got this for A1 and A2. I should just add them up to be able to get my A. So if I add them up, here we go. My A1 is going to be Vxit plus, and my A2 is half AT squared. If you did not smile by now, you really did not get the uniformly accelerated particle model, Big Kahuna. So here we go. So the area then is equal to half AXT squared plus VXIT. Let's refresh our memory. The Big Kahuna relationship was supposed to be XF equals half AXT squared plus VXIT plus XI. So, what must you conclude? The area must be equal to And if you did not say that, please think about it again. You'll be able to see that it is. So you see, the geometry also gives us some formulas. And it's the same formulas that we've seen in the labs. So, to summarize, the area under a curve then, once again, represents the displacement. Thank you.